I expect we'll continue to see more people joining, but we can go ahead and get started with an introduction and then move things along. And this talk is being recorded, so will also be accessible after today. So just to welcome everybody, we're hosting a webinar here. This is in anticipation of an event that we're having at Lehigh University in January 2023, as you can see on the slide. This is the SSMCDAT Hackathon, which is an event that is essentially designed to bring together people working in data science and or solid state chemistry, and to sort of come together and work on problems in the intersection of these fields. This is an event that doesn't require registration. It's NSF supported. So in terms of registration, there may be some travel support as well. So if you are interested, please visit the website that's listed on the slide here. We're still accepting applications for those that want to participate. And you can also see other webinars on YouTube and so forth like that listed on the website. Well, today, we're going to pass things over soon. We have, as leading up to the event, we have a series of webinars that we are giving in this topic areas. And today we have Professor George Karniadakis joining us from Brown. He is the Charles Pitts Robinson and John Palmer Barstow Professor of Applied Mathematics and Engineering at Brown. Is a long list of accomplishments. I'll give just a brief elements of it here. So he got his PhD at MIT, went on to positions at Stanford and Princeton, visiting Caltech and so forth. He's a fellow of a lot of the distinctions here, AAS fellow of SIAM, fellow of the American Physical Society, fellow of the American Institute of Aeronautics and Astronautics. Is won a variety of awards, including most recently, perhaps the SIAM ACM Prize in Computational Science and Engineering. He's got, I see on Google Scholar, over seems like 1,000 papers with over almost 72,000 citations. A lot of exciting work that he's been doing. Today, let me stop my share so we can flip over to his slides. Today, we're going to be hearing about his work on physics-informed machine learning, blending data and physics for fast predictions. So without further ado, let me pass it over to George, and thank him again for joining us.
Thank you, Frank. Can you see my screen and can you hear me?
Yep. Good.
Okay, I wasn't sure exactly what the audience is, but I thought I would start something that we all connect to. Actually, I'm drinking my coffee, as you can see right now. It's this time of the day, and I have this. I was able to, after many rejections of my proposal, to fund this through a private company. It's called LaVision. It's a German company that does visualizations and so they were very kind, and they used this Schlieren photography for a problem that is dear to my heart, as I said, and that is, I always wanted to know how fast the aroma will hit my nose in my espresso cup. In other words, I want to, from these pictures here, Schlieren photography to these slices, to quantify the velocity field and the pressure field with no other information, just the ambient temperature. Okay, so if you say that's not so important problem, but of course, what I'm suggesting is that this is a ill-posed problem. It's an inverse problem. It will go from imaging to quantitative information. So if I can solve this, I can solve lots of other problems, I think. There's lots of imaging in materials, in the structure of materials, and so on. I'm not exactly sure the specific interest that you're addressing in your initiative and consortium, but I think you get the idea. Having a thermal plume in a video, and can you extract quantitative information from this? This is not the most important problem in the world, you would think, although it's important to me personally. But the same problem is important for biomedicine. For example, my collaborator at Children's Hospital has this every day. He's looking at arteries. They put in some contrasting agent inside a brain artery, and they see if this aneurysm, the brain aneurysm, will rupture. So we published that work addressing this question in Science 3 years ago. And then for materials, you may be interested in detecting microstructure or even a crack, a surface crack, or an embedded crack in a aluminum alloy, for example. And this is from a hackathon I will describe later, which was a DARPA hackathon. There were 12 teams. I will tell you what happened. But this shows a ultrasound at an angle hitting this, I don't know if you see a tiny crack here. And the question is, where is the crack, how big it is, and so on. So these are some of the problems I want to look at it. Problems where there's data, there's not well specified, not everything is well specified, not exactly what we want in applied mathematics, but this all directly comes from applications. So for those of you who are not following the mathematics of machine learning, this mathematics was developed as early as late 80s or 90s. For example, the universal function approximation simply says that if I have an input X and an output Y, and there's a pairs of data, then I put here a single hidden layer, which is justified by these neurons. And then there's a linear input that comes in. We apply a non-linear, non-polynomial, as it turns out, the theory is a non-polynomial function, and this is the argument of that function. That function is called activation function. And then with a very simple construction, namely the output can be written as a linear combination of these non-linear bases now. It's linear, right? W are the weights that you're looking for. B are the biases, the offset. But then W2, there's no activation here. So these are linear. This part is linear. This is the non-linear part. So I can write the function, the output, as a linear combination. These are the output weights times this basis for one layer. And as I take n to infinity, the theory says that we can actually have an arbitrary close approximation to a function that describes this data. So that's known as universal function approximation. I want to contrast that later with something else. I will tell you about operator approximation and functional approximation beyond functions, something that my group has pioneered. So this was done in the, as I said, late 80s and 90s. Of course, now, today, in today's world, we work with deep neural networks. A deeper neural network means more of these layers. This is one hidden layer, a second and third, and so on. And because we realize that we can do it, because we have NVIDIA GPUs since 1993, but more recently, they have been powerful in accelerating progress in this field. The theory is the same, but here now I have an expression of the neural network, which again I can write it as a linear approximation of some basis, and this basis is the last layer, the last nonlinear layer will give me a basis. Now this basis is parameterized with the weights and the bias, but it is also obtained by the data. So it's really an adaptive basis that when you sort of match the prediction of the neural network with the output, you obtain this basis. And that basis in some sense is ideal because it directly follows the data. You don't have to change a grid. You don't have to do anything. So now this is nothing else but what we are familiar with other methods, spectral methods, Fourier methods. This is the basis, and these are the coefficients, just like the single layer. And of course, there's also a theory related to that. But again, the way to read, to interpret a deep neural network is a function approximation with an adaptive data-driven basis. And then you have these weights, which is the last linear layer. If you do classification, this last linear layer will change, but it's not really a big deal. So this justifies why one would need to use neural networks, because I get all that question all the time, why we want to do scientific machine learning or scientific computing using these neural networks, because they're very good approximators. And here's an example. Let's say I want to approximate a function, will be like a dislocation, let's say, in the material, have low frequency on one side, higher frequency on the other side. And here's the corresponding Fourier spectrum. What you see here, the red point is where the data, and basically what we're going through the iterations of this neural network through the epochs, and we see what the neural network is learning. So we take X-rays of what is going on through this Fourier transform. As you can see, there's some hierarchy. The movie will start again, but first it will sort of discover, so to speak, the discontinuity. Then it will go to the low frequency on the left. Then it works on the high frequency on the right, and you can see that on the Fourier spectrum. The interesting thing is that after it finishes this frequency, it goes back to the discontinuity. You can see a single point moving, and then it is adjusting the long tail of this spectrum, which is associated with the singularity. So it's really interesting because there are non-numerical methods that do that. I developed a lot of numerical methods in my 30+ year career, but none of these methods do that. So there is some advantage if you use it, if you use this method judiciously. So this is sort of the driving point of me trying to solve PDEs and simulating science and scientific problems using neural networks. So this brings me to physics-informed learning. It's something that we got a patent a few years ago, and that is most of the times, especially some of us who are in mathematics, we want to deal with problems like that, very sterilized. We pretend we know the physics, well-posed problem. We have characterize the initial and boundary conditions, and then we solve a forward problem. However, more often than not, you have to something like that. You know part of the physics, depending on the discipline, you may know more or less, and then you don't have details of some of the terms, for example, in reactive transport or in constitutive properties of complex materials, the microstructure, you don't know how to deal with it, but you may have some measurements. So think of this as the large scales and the small scales, but this can be interpreted in many ways. We have some physics, some data. Of course, there are cases where you have no physics at all, and you have just a lot of data, but that's typically happens in Facebook. And in science, we always have some prior knowledge, and the question is how you bring this prior knowledge in. There's many different ways. My group has been working on multi-fidelity learning, functional priors, and so on. But here I will describe the pins, which has been popular across different disciplines. And it's a very, very simple idea, the simplest idea we ever actually wrote a paper for. And that's why our original idea was rejected, and we kept going to another journal for 2 years until it was finally. Now we have close to 4,000 publication citations of this work in the last 3 years, because it's very, very simple, as I said. So what's the idea? Well, the idea is really just a neural network. So imagine you're looking at U as X and time. So this is a neural network like before. Sigma is the activation function. Here we have 2 hidden layers, let's say. So the mathematics behind it is very simple. As I said, this will be the labeled data, the data for which you have measurements. This is what the neural network produces at all these points. You iterate, you try to minimize this mismatch with respect to the biases, the weights and the bias which characterize these links. And then you set up an iteration loop like this on the left side. To do that, for something complex in 3D and time, you will need like 10,000 measurements, and you don't have 10,000 measurements. Okay, what you have, or you may know, that U may satisfy some sort of a conservation law from physics. For example, here I pretend that U also satisfies this nonlinear Schrödinger equation. Okay, so you can see that's a parameterized equation. I don't pretend to know the entire equation exactly. So lambda 1, lambda 2 could be unknown terms. Constants or non-constants, in fact. I can also have, I'll show you that later, I can have also a term that is a function I'm trying to discover. Now, f is the residual, and then if I penalize the residual, I'll have another term where I can draw data from. How do I draw data from? I can evaluate this term in space-time at random points, like doing Monte Carlo sampling. By doing Monte Carlo sampling, you can generate as many data as you want, and you can bias it. If they have dislocations and so on, you can discover them and you bias. So you can do adaptive Monte Carlo sampling, let's say, in space-time. I will give you lots of data. So now you take the real data, the measurements that you have. By the way, the data could be images or it could be point measurements. So or it could be constraints. Constraints will be going here. But this is the data, this term, and then this is the physics. And of course, you can combine them with weights in front, because you can combine, you can have more weight, more data, less physics, and so on. But notice that this very simple, if you do a linear combination of those two terms, you basically have a unified formulation for forward problem, for inverse problems, and for hybrid problems. And then in the process, what you will be doing, for example, you will discover the solution, but also you will discover these constants, which will become hyperparameters. The same way you compute the weights and the bias, you will compute also these parameters. So in this new framework, having 100 parameters to estimate is really trivial, because remember, here, the weights and the bias, which are hyperparameters, are hundreds of thousands. So if you add 100 physical parameters in the stack of these unknown parameters, it doesn't cost you anything. So in other words, you can sort of solve this equation with unknown parameters in the equation if you have some data. So that those two work synergistically, and you can see, in fact, the same code will work for the forward and the inverse problem. Now, what makes this very, very simple is the fact that how would you construct these differential operators? Typically, numerical methods, we set up a grid, especially if it's a complex material. Imagine you have these crystals, and you have, that will take forever. I call it the tyranny of mesh generation. Across engineering and material science, it's really, really tedious to do that. And you need to know a priori, in fact, the structure so you can follow it. Here, you don't need to do that, because all these differential operators will be based on automatic differentiation. Automatic differentiation is something that Google and Facebook are using in TensorFlow and PyTorch. It's basically computing the derivatives. It's not exactly symbolic differentiation, but similar. You construct these derivatives, all these operators, using computational graphs. Recently, DeepMind has come up with a really good way in a framework called JAX, J-A-X, which we follow. But I want to demonstrate how simple is this for something that we teach our students, namely this Berger's equation. It has advection, it has nonlinearity, it has dissipation, and so on. So time and space, t and x, are not discretized as in classical numerical methods. So x is continuous, t is continuous, and in this space-time domain, we're trying to solve the system. Now, where's the data? Well, the data is, they gave me data on the initial condition, because it's a time-dependent problem. They gave me some data on the boundaries. These are the black crosses, 100 points altogether. But notice they forgot to give me data here, or the sensor didn't work for a period of time. So can I solve this problem? The answer is no. You cannot really solve this problem with classical methods, because you don't have boundary conditions here, and there you have, unless you fill in zeros or something, but that's not the right problem. However, in this type of pins, we don't march in time, we solve an optimization problem. So how we go about this? See, this is the whole code. You can see how simple this is. It's so simple, a high school student can do it. So we define the neural network here in TensorFlow with weights and biases. Then we basically compute the residual f of this equation by taking the gradient in time and space twice. And then we put it together. Then this part here will be evaluated using Monte Carlo sampling. The data, the black crosses, will be evaluated through this term. And after that, you send to your optimizer and you're done. Where would this be evaluated? Again, this will be evaluated by taking random points in space-time. Just sprinkle points inside this domain, you can compute this term. So you have as many terms as you. So as you can see, 10 minutes later, you don't see the time, the clock on the wall, but 10 minutes later, you get pretty good looking solutions, which takes about 6 months to teach our students using other methods. This is 10, and also it avoids this basis. Remember what I said, the basis itself is an adaptive basis. If you try to do this with Fourier methods or other finite element methods, you get overshoots and undershoots because of this steep gradient. Here, the basis adapts to the data and the physics at the same time, so you can get pretty good looking solutions in 10 minutes, as I said. There's something very, very important that the entire computer science community has sort of ignored somehow, because most of the developments are coming from commercial machine learning, where people are interested in recommending new shoes and so on, seasonal shopping, and that's classification. But in regression, in science, you need regression. That's very important. And so the adaptive activation functions play a very important role. It turns out that they're mimicking the firing of neurons. But of course, if you look at human neurons or any animal neurons, you see that these are very, very sophisticated. There's a hierarchy. They fire different at different tasks and so on. So my group initiated this adaptive activation functions, which, depending on the data, each neuron will fire at different rates, for example, and each layer. So this is very important. We just published a paper on the archive on the history of this, because, as I said, activation functions, for example, the sigmoids, the hyperbolic tangent, the ReLU, which is like a ramp functions, are mimicking something very, very complex. And we pretend that this is great, but as I said, it's not exactly that. For multi-scale problems in physics, and we have lots of multi-scale problems, multi-rate problems, these standard activation functions don't work. Just to give you an idea, here we construct a neural network. Each layer has different activation functions, as you can see here. And now the activation function, the sigma, I call it phi now, is the sum of some, let's say if you take phi k as hyperbolic tangents, like I do here, but then on top of that, you add sinusoidal disturbances, and you will find these amplitudes of the disturbance and the frequencies, which will again follow the data. Now, why do you want to do that? The reason you want to do that is because the way neural networks work with back propagation taking gradients, if the standard activation function is like this, notice at ±1, you have Banchi gradients. So you're going to stagnate. You're not going to go to the minimum, to the global minimum. But this way, you sort of get out of stagnation, so to speak. You avoid plateaus in the optimization. And in fact, we have theory that shows that indeed, with this type of constructions, you can optimize learning, and also you will never get into a bad minimum. So, for example, we've done that in several physics problems, but here I show you that the standard benchmarks that the people using like CFAR 100 will be a classification of 100 different classes. We beat the state of the art, is the green curve, and so this is something that we published recently. Sorry, I don't give all the details, but the point is, I was trying to sort of raise awareness that in science, you cannot just use simple ReLU, which is like a ramp function. That's not going to work. Sometimes it works, but most of the times it doesn't. And if it works, it's better to use this to change the slope from one neuron to the other using the data. As I said, this is a very simple method, and in fact, a high school student worked on it recently. He wrote a paper with me, 40 pages, because he found this this field interesting. So he said, well, okay, you took this and you have the boundary conditions, the initial conditions, the physics, the data. Why don't you add another term to penalize also the gradients of the residual of the physics? And it turns out that that's a very good idea, because then you have smoothness, you have other mathematical properties, which are very good. So as you can see, he gave a talk to Brown last year, just before his English class from the library here, 17-year-old. And I wanted, and this is, he was doing a diffusion reaction equation, trying to find the diffusion coefficient, for example, from data, and something that we published before, but this is what my postdocs produce. This is what he produced in terms of the error versus the number of training points. You can see that he's much faster, more accurate, and it was a good humiliating lesson for my postdocs. He's now at MIT, a first-year student. Okay, I'll skip some of the other stuff, but now what happens if you have systems of equations? Like, for example, I'm interested in fluid mechanics, so we have momentum, we have constraints, and so on. That's okay, because again, the extension of the neural network to this physics, everything is in this box, which is the same parametric space. So if you have data for one, then you transfer these parameters to the other fields and so on. So for multi-physics problems, this is really interesting. And so you simply take again the data here, if you have any data. Then you take, by the way, you don't have to have boundary conditions. That's the point. You can have measurements anywhere. So this data term could be sporadic data anywhere, not on a lattice, not anything, and asynchronous in time as well. So that goes into this term. This physics goes in here. Other constraints, let's say monotonicity or something else, will go in there. And then you combine all this into a loss term where you have the physics, the initial conditions, the boundary conditions, and so on, then the data. So the multi-physics problems is not difficult. And that's exactly what we did with the problem I told you about biomedicine. The only data we had is the geometry, and this dye, it's a contrasting agent, visualization. This is the dilation of the artery, which was not supposed to be there. So we want to basically compute the wall shear stresses and the pressure, so to determine when this will go above a yield stress, let's say, and therefore the of the tissue, and therefore this will rupture. Right now, the doctors look at it and says, "Oh, I better operate on this poor guy." That's very subjective. So you can imagine what they do at Harvard and what they do somewhere in Africa. It's totally different. So because of the budgets, but what I'm saying is totally qualitative. So what we do is we actually encode this imaging, this video, into an equation that looks like this. I is the intensity, and that is advected by the flow U and V and W here. Then we write an equation we think that is appropriate. For example, here we have the non-Newtonian flow equations with some incompressibility. And from that, just from the intensity, we try to discover the physics. And so, for example, you can see here, these are slices. We're looking inside the cavity, this aneurysmal sac, and we can totally infer the flow. And just as a verification, we did also a simulation for the forward problem, pretending we don't know the inverse problem, and you can see what you learn just from the dye visualization, and the exact solution is amazingly close for this very, very complex field. These are streamlined swirling flow and so on. So we can do that, and if we can do that, of course, we can do the coffee. In the coffee, what we have is slices of the temperature, or the gradient of the temperature, but temperature above the coffee example here. We match it, that's our data. By matching it, we learn the neural network, this whole neural network that shares parameters. Therefore, I can get the pressure and the velocity all in one shot. So this is the first time that somebody wrote about flow over an espresso cup in the Journal of Fluid Mechanics, which is our main journal in. Okay, going back to materials. So this is the hackathon that DARPA had a couple of years ago. And they were basically giving us video of ultrasound hitting this surface crack. You're not supposed to know which the orientation and where is it. So the question is, where is the crack, how big it is, and can you find exactly the shape of it? So they gave us quite a bit of data in the video, and the 11 teams says they didn't have enough data. I said, we have too much data. I'm going to use only 10% of the data from one of these pictures. I don't need all of this. I just need 10% of the data, and then I will try to determine exactly the geometry of the shape, the location, the orientation of the crack. And how did we do that? So this is what you have. Basically, the ultrasound, there is some microstructure here. There is reflections, as you can see. The real data is on the left. The pin gives you, matches the data in an amazing way, as you can see. It's a slow video because there's lots of frames, but you can see the reflections just in the real life on the left. This is what so we know that we get to the right thing. Now, what we do is we introduce also physics, wave propagation through the material. And since the material, they told us, is heterogeneous, the speed of sound C will depend on X and Y. So now what we do is we create this loss function from physics and the data. The data is the video. So if I go back now, I have a pin which solves this equation. And then this C depends on X and Y. And for that, I will have another neural network with different parameters theta. So in my optimization problem, I will determine, I will have enough data, I will determine the theta, the parameters, which is the weights and the bias of the pin, but also the neural network. In other words, I represent its unknown function with another neural network, not another pin, another neural network. If you determine for a neural network these links, the weights and the biases, then you're done. You know exactly C of X, Y. If you set that equal to 0, you will get the contour of the crack. That's what happens, and you can see it up here. Most of the material is constant. The speed is constant, and we verify actually with the. But then we can get exactly right here the material. So the reason I'm showing this example is because, first of all, it's realistic. It comes from a hackathon, and we publish it in this Journal of Non-Destructive Evaluation with with the people. Their co-authors are the people who set up the problem from Air Force Lab at the in Ohio, in Wright-Patterson. So they didn't know anything about. They just had the data, but basically to show that neural networks and pins in particular allow you to determine not just constants, but functions which are known, part of the physics. That's very important because it can characterize things that. So it's up to you to. Okay, so I have something that could perhaps be related to what you guys are doing, and suppose you're looking at certain material or the same phenomenon, and you have historical observations, right? From so then you have very few new data, but you have historical observations, and you may also have some physics. So you set up this functional prior in a Bayesian framework. PI-GAN means physics-informed generative adversarial network, something that we published before. So you put this, you dial in some noise into this PI-GAN. PI-GAN is more like semi-supervised learning. You have this historical data, and then you have some of the physics, and what you get is you produce very informative priors in the Bayesian framework. Instead of ad hoc priors, no, you now bring all your prior knowledge that satisfies the physics and your historical observations into a functional prior. You don't commit to a state yet, but this is just a prior. Then you have some data. For example, here I solve an equation for the U and the F. So I have the left-hand side and the right-hand side. I have, let's say, 2 new observations for the new material for the left-hand side and 4 or 5 on the right-hand side. And then I use a generator again to create more data, so I can calibrate basically my posterior. If I have my posterior, then I can do everything. Just to give you an idea how powerful this is the area of meta learning. I don't know if you've heard of meta learning. Is learning to learn, but this is a nice example of, let's say you have a distribution like this for A and omega, so you create a prior like that. Okay, so you have a consensus, so you can build a consensus neural network that follows this type of distribution using the method I told you. So that's sort of the functional prior. Now, somebody will give you data. For example, in trying to discover this new function here, you have 1, 2, 3, 4 data, but you don't have data at all here. This is totally gappy. And notice if you use Kriging or Gaussian process regression, you get obviously what you expect. You get the 0 mean, and you get a huge uncertainty. But with meta learning, you get the right thing. This is a dot crossing. Something with this pink line is something that the state of the art in what's called model agnostic meta learning. What they did before, Chelsea Finch is a professor at Stanford in her PhD thesis at Berkeley. She took a mean of these. She just kept a mean of all these, and then she started with that, and she does a pretty good job, but actually not perfect. What we said is you actually can keep all the distribution, and you can do a better job. This is another example where you have a diffusion reaction equation. I don't know where it's diffusion react. Now we don't know anything about this reaction constant, but we know its distribution, but we don't have any data at all. Instead, what we have is 10 random observations on the right-hand side and 2 random observations of U. We know D, but we don't know this, which is a function. So there's no way you can solve this problem because you only have 12 points, 12 measurements. But you have these distributions of the right-hand side and of the reaction constant. It turns out with this method of functional priors, you can get the F of the right-hand side, you can get the solution U, and you can get the unknown reaction constant, which is a function, And you can also get the uncertainty, which is a nice thing. So this functional priors is actually a very powerful approach. It extends, in some sense, the Bayesian framework, where you have really informative priors, not ad hoc priors, using historical data, observations, handbooks, and so on. So there's lots of pins. I don't want to get you into the math mode, but we can deal with noise and so on and so forth. There's a library, if you are interested in this, to get started. There's a library, has been downloaded over 300,000 times from GitHub. It's free. And there's a tutorial also from Science Review. But basically, it's a code of about 100 to 150 lines of code. Anybody can learn that. I joke because I say even professors now can implement their own ideas. You don't have to program too much. So this is in TensorFlow or PyTorch. All these frameworks are very, very useful. The industry is all over this. NVIDIA, ANSYS, and many. I work mostly with industry these days. I'm giving a talk to Shell tomorrow morning. Okay, so I have some more time. I can right. Let's see, 37 minutes. I'll go another 10, 15 minutes. Is that okay, Frank? Yep. So I told you about having data as an input and data as an output. And then, of course, a function will map the input to the output, right? That's a function. And we approximate with using neural network. We have the theory. What about having functions as an input? This is motivated by some challenges that my daughter had in learning calculus. So she asked me to develop a neural network that takes functions in and gives the functions out. That, of course, will be an operator. It could be an integral, it could be a Laplace transform, it could be an ODE, a PD, or a black box mapping, if you like. But if the input is functions and the output is functions, so you can imagine the output will be a stress field. It could be a concentration of some species everywhere, kinetics and so on. So this now is the operator. So we basically now have to find an operator at a higher level of abstraction. So there's some resemblance of what I have here to human neurons, because these are called branches. And this is my inputs called branch. There's a soma, there's a trunk. And then the output here, these two neural networks will work together, just like the branches work here, and there's a synaptic output. It's a little bit of sketch, but that's what we published in a couple of years ago. So just to reflect what we're doing, 99.9% of machine learning does this. They take some data from some space and map it to another finite dimensional space. We are sort of changing the paradigm. We say, can you go from a function to a function? Now, why you want to do that? Well, in real life, it's very expensive to train one neural network to do just one condition. So imagine you have many, many operating conditions, a material that's subject to different temperatures, different loads, and so on. So you want to pre-train all this, and then in real time, you can infer new conditions. So you have a new condition, you don't want to retrain again, because that will be too expensive. So we're trying to use the higher level of abstraction, where we pre-train everything in a higher dimensional space, and therefore we need to approximate operators. And the question is, can neural networks approximate operators? A question I was asking 5 years ago when I was teaching my class. And it's funny how science is this year. You know, go to a blog and you read about it. Says one guy says, "Oh, cool, I can do it. I can approximate the derivative." The other person says, "No, you cannot. There's no theory," and so on. But anyway, thanks to good mathematics by Chen and Chen, professors at Fudan University in Shanghai, they actually wrote a paper that nobody ever cited in 1995, saying exactly, answering exactly my question, that if you want to map a function to another function, g of u of y in the output space, and g is a nonlinear continuous operator, then again, there is a single hidden layer. You don't need a deep neural network. Single hidden layer can be used to approximate this operator using this double summation. So now this double summation, you see sigma here, you see sigma here. This is the input space. U is the input, which you sample at some points. And then sigma applies to the y, which is the output. So this is there are two neural networks, just like I drew them in the sketch. And that what I had in my sketch is basically the theorem. Okay, so independently we arrive at this. In fact, we implemented this, which was never used before. We implemented a neural network. This is a branch. This is a trunk. This is the output space, the input space. If you cross them, you get functions. You get whole fields, stress fields, kinetics, velocities, whatever displacement and so on, whatever really you want the output. So it's very powerful. The only problem is, how do you train operators? Because single layers, and we know now today that if we're interested in high dimensions, parameterized equations, we need to go to deep neural networks. So at that time, there were no deep neural networks. So I extended actually the theory to have deep neural networks. We replaced the single layer with a very deep neural networks, which are very, very expressive. And we proved that the theorem, I will save you of 120 pages of theory. We proved that we actually can beat the curse of dimensionality because it takes a lot to learn an operator. So you don't need a lot of data to learn an operator because that will break the bank. And I will demonstrate that. So if we concentrate here on panel B, what basically is saying that you start with a function U, which you characterize at this point. So you have to have very well characterized inputs. But then at the output, we observed, and the theory later showed, at the output, you don't need to compute G of U of Y at many points, because this will be your label data. This will be your experiments. This will be your videos, the measurements. You just need a couple of points for each excitation. Then you take another excitation or another forcing condition, and then again, you evaluate at one point and so on. Do that maybe 1,000 times, and then you're done. You learn this operator G. Then, given a new excitation, I should be able to infer the output without further training. It's very important. In all these pins and all neural networks, you need further training. But here you exhaust it, the search space. You can always go back and enrich it. But so here's an example to answer my daughter's problem. So I want to map U of X to this indefinite integral S of X. U of X is an integrand. S of X, X is an interval from 0 to 1, or we can make it from 0 to infinity to cover a Laplace transform. So I take 10,000 functions, U of T, from some distribution. So I have 10,000 conditions. You can, the way to interpret this, I have 10,000 forcings, right, that I do offline. And then for each forcing, I evaluate the integral only at one point, not in this interval, because it's indefinite integral. So I only compute S of X at the X star, let's say. I do 10,000 times, 100, but I need to have 100 points to characterize my input very well. And then after I'm done with the training, you can see mean square error. There's a number of iterations. I can learn this 10 to the minus 5, 10 to the minus 6 accuracy. You can improve it if you like. But the point now, if you give me a function at 0 time, like a fraction of a second, I can tell you it's indefinite integral in this or other, or it's Laplace transform, and so on. So the idea is, of course, to extend this to real applications. So this is something that is used as a benchmark for those who do stiff kinetics or chemistry. So what is this? There are a system of 3 equations here. It's called the Robert problem. We use it in some applications that I do with a company for detonations for now. But notice that K1 one of the reaction constants is very small. K2 is very big, and K3 is also very big. So there's a huge disparity in the reaction rates. So what we do is we have here what we do, we map the initial conditions. Basically, we want to replace the system with DeepONet. So after we train it, we call DeepONet to do chemical reactions for us. Okay. So we trained for a plurality of initial conditions. And of course, we have corresponding answers. How do you find the answers? MATLAB and so on. But you do that, at night when things are quiet. So you have time to do that. So offline training. And then time here is the output domain. But here in the output domain, you can have time, or you can have another parameter, for example. So you can parameterize that. But anyway, so notice what happens. We have this plurality. This is Y1, plurality of Y1, and then we map it to some conditions. So instead of taking time steps 10 to the minus 6, and so on, I go in a huge time step. I can go directly there, the final product, as you can see here. And for Y2, I can have stops. I don't have to go all the way here because there's nothing. It has that species has been consumed. So I can jump from the initial or these initial conditions to some intermediate level or here or final and so on. So the point is, DeepNet allows you to go from one distribution to another distribution without further training this. The same thing for this used for pollution, chemical reactions in the atmosphere is now 13 species. Same idea again, and you can have some of the unknowns actually being, some of the Ks being unknown. And again, you go from a plurality of conditions to something else. Notice that I train here on the left, but I predict way outside. So I actually extrapolate. Same thing for all the species. So you train in one range of initial conditions, you can actually extrapolate outside. And most of the times, this is pretty accurate depending on the distribution and so on. And then I have one more example to show how DeepNet can predict bubbles. I didn't know what examples to choose. I have some on materials, but I didn't have time to show you, and I didn't exactly know what materials you're doing. But anyway, here we grow bubbles. We can use video. We can have a let's say this equation that grows bubbles in the continuum. So R is the radius of the bubble. There's some pressure difference between the bubble and the ambient. So this nice equation by Lord Rayleigh, it has kind of very accurate equation on growing spherical bubbles above a micron. So the way we train a neural network, the question is, can DeepNet learn this whole operator? Okay, because if it learns, then you give it another pressure distribution, it can tell you how fast the bubble will grow. And so we train it here. We take the pressure difference as a time is the coordinate, and R of t is the label output. So after we train it, let's say, I don't know, here 3,000 times, you can see now here I have some arbitrary pressure distributions. And for 3 different cases that I have here as a test, this is the radius versus time. You can see it's a multi-rate dynamics. The bubble is not trivial. It breathes very quickly. Different pressures will give you different slow and fast dynamics. So DeepNet can very accurately give you that at 0 time, basically 0.01 seconds, something like that, because it interpolates the functional space. Now, this equation can be solved very quickly in a MATLAB, so you don't need to do that. But imagine you are doing nanobubbles. Then you need molecular dynamic simulations, like when we model materials, an MD or even below. So we wanted to grow bubbles from the nanobubble to the big bubbles and above micron. So this is the initial radius, right? So this equation is valid here, but we don't have equations like that here. Instead, we do molecular dynamic simulations here. One molecular dynamic simulation for a bubble takes 50 hours on 32 processors, okay? So you need somebody patient to ask him or her to do 50 simulations. We did 50 simulations in this regime, and then we blend this with the continuum, and now, first of all, you can see here the stochastic fluctuations. We can learn the radius of these nanobubbles. Stochastic fluctuation is more difficult to learn, but it is possible. And then we can put all together the continuum thing of this initial radius. This is the atomistic regime. This is a continuum regime. We throw all this data, continuum and atomistic, into the DeepNet, and DeepNet can give you the continuum regime now. It can give you the atomistic regime. It can give you the interface without any intricate handshaking between the continuum and the atomistic regime and other things that we use in multifunctional materials when we're trying to bridge the scales. DeepNet, and now here for this nanobubbles, you can produce the answer in 0.01 second as opposed to many types. So, in conclusion, what we have is a DeepNet is a higher level abstraction. It can take as inputs, the branch can be a CNN if we have images. If we have historical data, it could be an RNN. The neural network could be a graph neural network, but it does have some similarity and resemblance with human neurons. But the DeepNet provides a plurality of different types of operators that can be designed and lots of things. I also want to say something about the course that I developed for NVIDIA that will become free to all educational institutions. It's called Deep Learning for Scientists and Engineers. It's probably the first course that on machine learning that will have no dogs and no cats for classification, and everything's about science and engineering. And you can see here the modules. It's all about tools, the first part, pins, uncertainty, and so on. And then we have 20 different projects across different disciplines, geophysics, and I think materials that students would. So this will be a free from NVIDIA. They have a teaching institute. They try to reach to do outreach and so on. So this is based on our work and so on. So my sponsor is the Department of Energy. We have the first ever we established films collaborator in physics and for machine learning. We just got renewed to do more with operators and graph neural networks. And then also we have a MNURI on pins and learning and meta learning. I talked to you about meta learning a little bit, but we have Utah actually. Mike Kirby is the PI with Shandian Jie from School of Computing of Stanford and Caltech as our partners. And with that, I'll stop here and happy to take questions.
Thanks very much, George. I'm just personally excited to hear a lot about, like you said, machine learning without just classifying cats and dogs. It's exciting. So for anybody that is on the call, if you'd like to post a question in the Q&A, that would be the time to do it. We have a hand up, but let me see.
I cannot see anybody, Frank, except you and Taylor.
Yeah. I think if anybody would like to ask a question, you can raise your hand, or you can post it in the chat, Q&A chat. I think while we're waiting, maybe for questions, let me just ask one myself, and then I'll turn it over to. So, in the discussion of pins, I don't know if I'm formulating this question right, but you mentioned how you could basically sort of learn, say, parameters involved in the physics, and sort of like hyperparameters and so forth. Have you seen or had any experience of cases where you sort of have the physics wrong and you still try it, or maybe extra terms? Like, and I guess I wonder if it's good if during the training would somehow discover a sort of the right physics. It would zero out certain terms if they're not needed. Things like that.
Yeah, that's a good question. So for model misspecification, you have to be very careful with model misspecification. That's the answer. Hopefully, if the model is misspecified and data is right, then this will not converge. So you're not going to get garbage. But unfortunately, in this field, you're looking at the landscape physics and data, and it has too many valleys and peaks. So you're going to land to the wrong valley very quickly. So it's very important to bring in disciplinary scientists to do this right. And so if you don't know the physics, you do exactly what you suggested. You add terms with parameters in front, which then the pin will tell you 0. So we have many examples actually where we over-parameterize the physics, and then we let the data decide. For example, in my case, when I was doing the fluids, if I don't know if the flow is non-Newtonian, I let it be non-Newtonian, and then that non-linearity will be 0. The extra term will be 0. And
do you need sort of to include somehow like sparsity promoting things in the
well, not really, because I know what you're after, Cindy stuff, but that actually is a second step after, because what you're finding here, there's no problem with data here, and there's no problem. What you will find here is a neural network. So you don't need to do sparsity. Sparsity and so on can come if you learn a DeepNet, and then you need to know from DeepNet you want to write actual equations, because DeepNet doesn't give you equations. It's an implicit operator. But if you're the old school and you want to write down equations, then you do that kind of Cindy, where you produce lots of data, you have a dictionary and so on, and you find it is possible.
So I have a couple of questions here. I guess one maybe is the easier one is when is this course on pins going to be launching or available? that you
I
mentioned?
think I'm not sure they will probably announce it within a couple of months. The course is available, but they're checking the lawyers and everything. We actually had to draw every figure ourselves, all the sketches, because they don't want to. But yeah, in a couple of months, and so NVIDIA have their own code called Modulus, and they want to include that part in the. I will be teaching this course at Brown, so I'll have my own academic version, but they won't without the without the NVIDIA stuff there. But so that can also be. I'm allowed to distribute that.
Another question we have, maybe this is pretty open-ended, but for someone who's in their early career looking to jump into the field, what do you find are some of the more exciting open questions to be addressed next?
I think scaling up, a lot of people trying to scale this up to real problems, and how do you do it, and do you abandon everything you have? There is these philosophical questions at least in engineering. Should we abandon finite elements because this looks so simpler? And the answer is not yet, because some sort of a hybridization of existing tools with these tools would be appropriate. For example, we published a paper where we're looking at crack propagation. And for crack propagation, if you have molecular dynamics, it's just like the bubble I said. You would need huge resources, right? To resolve the shock at the crack at the molecular level. So you replace that with a neural operator, but outside it's elasticity, finite element, pretty good. So you hybridize finite elements, for example, with this. There's another project I do with these detonations. You don't have to change the existing software that the industry or the government is using. They have big solvers, but the kinetics, the stiff kinetics that I demonstrate, the time step is 10 to the minus 6 as opposed to 10 to the minus 2. So you replace the kinetics with DeepONet, then you accelerate this by 100,000 times. I did that for a hypersonics project for the DARPA, and we obtained 100,000 times faster results because we replaced the stiff parts with the DeepONet. So I think how to bring in, how to avoid the hype, it's one thing, and then bring in what is useful for science and different scientific problems across discipline. That is where people could make their name and get tenure and do lots of other things that is happening. I think that there is a lot of room for that. I think for those people who do optimization, DeepONet is a very good tool for that. Lots of companies, and also I use it for some of my projects. We demonstrated that we can navigate 256 drones in a closed, crowded environment without hitting each other, going to as fast as possible to a certain target in 1 hour, in 1 GPU hour, something that Navy cannot do. They do it in they do like 20 or 1 dozen drones in a couple of days. We did 256 in 1 hour on GPU. So there are certain advantages. There's also disadvantages. There's some complex forward problems we cannot solve yet, and there's something called spectral bias in neural networks. High frequencies are difficult to resolve unless you design neural networks with feature expansion to include that type of frequencies that you expect, the wave numbers that you expect, and so on. So there's a lot of open questions. It's not, this is sort of the big, for us, was to sort of go beyond the cats and dogs, beyond classification, make this a regression tool. Then classification is very important too, and you can use regression, but regression is more demanding, as you can tell.
Thanks for that.
Sorry, Frank, I just forgot to mention there's a very nice paper published October 7th in Science, the search for high entropy alloys. I don't know if you saw that, using active learning and physics-informed learning.
Oh, okay.
It's a really, really nice paper. And they use thermodynamic principles. They use that. So it's inspired by pins, but they use thermodynamics principle to reduce the huge space using active learning. Active learning, and if you don't bring the physics in, you cannot do it. So it's October 7th. The quest for alloys, but high entropy alloys where you have equal composition of titanium, zirconium, all that kind of stuff. I use it for I just use it for one of my army projects actually, for choosing materials for hypersonics.
Great, thanks. I don't see any other questions, and we are at the end of the hour, and I just ensure people maybe have to move on. And of course, George, you're so grateful that you gave an hour of your time. I don't want to keep you too much longer. So thank you again for the informative talk, and we'll be posting the recording. And thanks for everybody who participated. Thanks.
Thank you, Frank. Have a good day.
Thanks, George.